everyone. Bill Cline here, Extension Specialist with North Carolina State University. This session will cover blueberry freeze protection using overhead irrigation based on some of our experiences in North Carolina. Before we begin, I'd like to acknowledge a couple of the pioneers of blueberry freeze protection, Dr. Ron Sneed and Dr. Mike Mainland at North Carolina State University were some of the early experimenters with blueberry freeze protection, and a lot of the information you'll see in this presentation comes from their work. Our discussion today is about freeze protection. You may hear the terms freeze and frost used interchangeably, but frost means ice crystals on an object that is at or below 32 degrees. Damage occurs to blueberry flowers and fruit at around 28 degrees. There may or may not be ice crystals on the bush at that critical 28 degree temperature. What frost does indicate to you is that it is in still air, there's no wind, and the freeze is a radiative event rather than an advective freeze. Blueberry freeze events in North Carolina pose their greatest threat in March, April, and May, during and after bloom. Commercial fields in southeastern North Carolina tend to be in low elevation sites, so those fields can have temperatures that are 8 to 10 degrees colder than the predicted low temperatures, so temperature has to be monitored in the blueberry field. We also find that overhead irrigation does not work very well on windy nights, advective freezes where the wind is blowing, and these tend to occur in March. Overhead irrigation works quite well to protect against radiation freezes or still nights in April and May. So, how does freeze protection work? We rely on the phase change of water from liquid to solid, from water to ice, to release heat. Freezing water gives off 80 calories per gram of heat. This is the latent heat of fusion. Now, this is a benefit that occurs only under conditions when humidity is high and the water is not evaporating too rapidly. So the goal is for the ice to stay wet all night, the irrigation runs all night and never stops. You constantly give off heat as the ice forms. We know that damage would occur at 28 degrees Fahrenheit, but as long as clear ice is constantly forming, flowers and berries under the ice never fall below the phase change temperature of 32, even if the air temperatures drop to the low 20s. What happens when overhead irrigation doesn't work for freeze protection? The most frequent cause is evaporative cooling that takes place during wind-borne freezes. If it's too windy, the ice on the bushes is white rather than clear. This indicates that the ice is drying and there's a tremendous cooling effect from evaporation of water. So if the ice does not stay wet and the ice is not clear, then you have cooling rather than the warming effect from the phase change from liquid to solid. Impact type sprinkler heads, usually brass, are used for overhead irrigation, for spring freeze protection, and for summertime evaporative cooling. Spacing is typically 12 per acre, and each nozzle puts out 5 to 6 gallons per minute for about 68 gallons per minute per acre. Blueberry irrigation systems in southeastern North Carolina rely on surface water from dug ponds. The pond is sized to the irrigation system based on the volume required. A single pump and pond combination may irrigate as much as 25 to 30 acres on a single system. Nozzles are typically a 5/32 orifice operating at 60 psi. They will wet a circle 90 to 100 feet in diameter at around 5 to 6 gallons per minute. Gallons per minute can be converted to inches per hour. The goal in North Carolina systems is to have approximately 1/1500ths of an inch of water per hour. This is again using 12 sprinklers per acre at 5 to 6 gallons per minute each. This table shows the precipitation rates in inches per hour for selected nozzle capacities and sprinkler spacing. The red star shows the typical North Carolina placement, about 60 by 60 feet, and putting out about 0.15 of an inch per hour. Some systems further south, some of the Florida systems that have to run irrigation during windborne freezes will put out double that amount. So you'll see systems that are designed for 0.31 of an inch per hour. The North Carolina systems, based on around 0.15 of an inch per hour, have known capacities at various minimum temperatures and wind speeds. So in this table, we see that with a wind speed of 0 to 1 miles per hour, the system should protect down to about 20 degrees Fahrenheit. As the wind speed picks up 2 to 4 miles per hour, our North Carolina rate would protect down to about 24 degrees. Once you reach 5 to 8 miles per hour, our North Carolina systems would work down to about 26 degrees. So as the wind increases, more and more water volume is required for less and less protection. This graph shows a typical radiation freeze event that occurred April 19, 2001 at the NCSU Ideal Tract Farm in Castle Hayne. This is a classic pattern where the temperature in the blue line drops very quickly after dark, and at the same time the relative humidity, shown with the red line, goes up and reaches essentially 100% by daylight. So the highest relative humidity and the lowest temperature are right before daybreak. And this is the scenario where overhead irrigation works quite well for freeze protection, with no wind, high relative humidity, and temperature falling to its lowest point just before daylight. Following the freeze event shown in the previous slide, we followed up with the cultivar powder blue at harvest in July of 2001, following that late spring freeze event on April 19th, and saw a tremendous difference in unprotected versus freeze-protected bushes on the same site, same field. So you can really make a huge difference in a single night, and the growers will sometimes remark that you can pay for your irrigation system in a single night, and this is an example of that sort of freeze protection success. Unfortunately, sometimes freeze events are not limited to a single night. Some of you may remember the 2007 Easter freeze. Over half of the North Carolina blueberry crop was lost. Prior to the freeze, the crop was estimated at over 30 million pounds. Surviving production in 2007 was 14.8 million, so about half the crop was lost. Only those sites with 3 and 4 nights of continuous capacity for overhead freeze protection were able to save the crop. So multiple nights of freeze protection may be required. Following a freeze event, you'd like to be able to evaluate the crop and see how successful the freeze protection was. This picture illustrates on the left a healthy freeze-protected berry that has white ovules inside versus a freeze-damaged berry on the right, where the interior of the berry is brown. You may have to cut the berry open to see this in the early stages. In this image, we see healthy, undamaged flowers on the left that we have cut open to show the green, healthy interior of the flower and the white ovules inside, compared to the damaged flowers on the right that are browning and water-soaked within 48 hours after the freeze. Damage from spring freezes may persist in ripe fruit and affect fruit quality at harvest. These near-frozen berries may ripen and yet have hollow, soft, or corky internal damage that is only evident when you cut the berries open. Freeze damage can also appear as a frost ring or a scar around the calyx end of the berry that can cause the berries to split as they expand. This image shows the freeze ring on the right 48 hours after the freeze event, and then 1 month later at ripening you see the berries with brown scarring and cracking open at the calyx end. Injured blooms following a freeze event are more susceptible to disease. One of the most common problems following a freeze event is botrytis flower blight. In deciding whether to run freeze protection irrigation for an individual event, it's useful to look at flower bud development in the field and try to estimate at what temperature damage will occur. If the predicted freeze does not go below the damage threshold for the flower bud stage, then you can wait until later in the season to begin freeze protection. This chart of blueberry growth stages has some good pictures and estimated temperatures of injury. This is from the pocket guide for IPM scouting of high bush blueberries at Michigan State. And this graphic carries throughout the bloom season and illustrates the various stages at which injury might occur. Blueberry flowers become progressively more susceptible to freeze damage as they emerge and open. Partly expanded flowers that are not yet open can tolerate 23 to 25 degrees. By the time you reach full bloom, the flowers will tolerate 28 degrees Fahrenheit. The most susceptible stage, after the flowers fall off and the small green fruit begins to develop, the threshold for damage can be as high as 32 degrees Fahrenheit. The risk of freeze injury drops off dramatically as the berries begin to size, and by the time you're in a medium green fruit stage, you should be able to see how many berries persist on the bush. Usually badly freeze damaged flowers and fruit will drop off 2 to 3 weeks after the injury at most, and you'll be able to evaluate the remaining crop. In addition to the growth stage of the crop, the potential for wind during a freeze event is a major determiner on whether to run overhead irrigation. This map shown with the isobars across the country indicates wind speeds. Where the isobars are closer together, the wind speeds are higher. Note the big blue H over North Carolina. On a night like this, with the high directly over the state of North Carolina and no isobars between us and the center of the high, we would expect the wind speed to be 0 and the risk of a radiative freeze to be very high. Dr. Mike Mainland created some drawings to help us understand the effects of the high pressure system on overhead irrigation success. This drawing shows a 7 a.m. on day 1, and the high pressure system is over the Mississippi, not quite to North Carolina. The blue star in our illustration shows the farm that we're trying to protect, and you would expect wind on this night, and it would not be an optimal freeze protection night. The following day, 7 a.m. on day 2, the high is overhead. The wind dies down, cold air settles into low areas, and this would be a night to be prepared to run irrigation from dark until the temperature rises again the following morning. By the 3rd day, 7 a.m. on day 3, the high moves offshore, wind increases, and the temperature rises. But sometimes the high will stall overhead, and the 3rd night can be the coldest. So just have to monitor the movement of the weather system and the temperatures and wind speeds throughout the entire event. The field thermometer that Dr. Mainland prefers and that we continue to use and have in our fields today are the Taylor minimum registering orchard thermometers. These are still available and still quite useful for monitoring field temperatures during a freeze event. The Taylor thermometers show the minimum and the current temperature, where the red liquid is at 90 degrees here and the black slider is at 82. So you can see the low was 82 and the high was 90 in this illustration. Even a slight rise in temperature during the night, you can see the red liquid start to move up, and this can tell you when the temperature is shifting. So these are very useful thermometers for monitoring in the field at the time of the freeze. It is important to calibrate your thermometer, even if it's a brand new one, just to make sure that the temperature that you're reading is accurate. We'll typically do this in a ice water bath, lots of ice, very little water, and do it inside a cooler or refrigerator so that you can get the thermometer to exactly 32 degrees and then see if it's reading accurately. Field monitoring thermometers are mounted at bush height. covered with a shade to prevent direct sunlight. If the thermometer is reading a little bit off, we just attach a tag to that thermometer with the correction factor written on there, so whoever's reading the thermometer knows to add half a degree or subtract. This drawing shows the thermometer mounted at bush height in a shaded holder about 5 feet off the ground and facing away from the sun, so facing to the north so that there's no direct sunlight on the thermometer. So to summarize our comments about the system design, we're looking at a system that will provide 1/1500ths of an inch of water per acre per hour, which is 68 gallons per minute. The maximum sprinkler spacing is 63 by 60, or about 60 by 60. The sprinklers are 5 30-second nozzles, providing a wetted diameter circle greater than 90 feet. The design is for a low pressure pump that will deliver at least 55 psi with less than 10% variation between the sprinklers. So you'd like to have all the sprinklers putting out at the same pressure rather than variation across the system. The way you achieve this is to size the pipe based on flow rates at or below 5 feet per second so that the system is a low pressure design throughout. Ideally, you'd have water for more than one night of operation. Desirably, you'd have 3 nights of 12 hours each. So this would be 31 hours from a pond and 5 hours worth of recharge from a well. A well capacity of 4 gallons per minute per acre is needed. And after the 2007 Easter freeze, we have growers now who have water capacity for 4 or even 5 consecutive nights. Based on the risk encountered in that event. Prior to a freeze event, the day before, we run the system and check all the nozzles. If more than 1% of them clog up, we'll shut it down and then crank it back up again until we have all the nozzles putting out water freely. Typically have to have lots of gear for that night, rain suits, boots, spotlights, something to unclog nozzles with, nozzle wrenches, spare sprinklers. We'll typically check the drainage around the field and make sure drains are open and check our shielded minimum thermometers to make sure everything's reading correctly. On the night of the freeze, we try to project what the temperature will be by daybreak and only begin the system, only start the irrigation if we anticipate a temperature below 28 degrees before daylight. So on a still night with low humidity, that means you have to make your decision and get the pumps running by 33 degrees Fahrenheit. If the humidity is low, you have to start at a higher temperature. So on a low humidity night, the temperature drops really quickly and you would need to start up at 36 to 38 degrees. The idea is to thoroughly wet the bushes, then reduce pressure so you can keep them wet. As the temperature falls, you increase pressure on the system so that the output is maintained. And then as you get close to daylight, use all the pressure that you have and all the coverage you can get. We will typically run the irrigation system the next day, long after the sun comes out, until the ice begins to melt and the temperature goes above 40 degrees. When you're evaluating whether to turn off the irrigation system, the ice should be slipping freely off of the stems so that the ice will fall off when you handle it. You can see water running underneath the ice. And you want to make sure the ice does not refreeze on the bush. If freeze protection irrigation is not done properly, it can be more damaging than doing nothing. So you really have to bring everything together with the system design. Choose your nights to run based on the projected temperature, whether wind is anticipated. You have to start protecting on time and avoid shutting down too soon. Some nights you'll turn the irrigation on and the temperature never comes up the following day, so you wind up having to run the irrigation all night, all the next day, and all the next night until the temperature comes up. So that has to be something that you plan ahead for. Otherwise, you run out of water or you have a system failure, and then you've done more damage than doing nothing. Within the parameters described in this presentation, freeze protection has been very successful for us in North Carolina. Probably 90 to 95% of the farms have overhead irrigation for freeze protection, and in most years get some use out of it. Again, one of these systems will pay for itself in a single night because of the high value of the blueberry crop that you're protecting. The information in this session is also available online in printed form, blueberry freeze damage and protection measures. Thank you for your attention, and I hope this has been useful.